Good morning, students. In today's class, we will discuss about different control schemes. So far, we have covered feed-forward control system and feedback control system. Most commonly used control schemes are feedback control system, and there are certain disadvantages of feedback control system. So where the certain tolerance is not allowable, then for the special cases or delicate systems, feed forward control systems are used. Apart from these basic feedback and feed forward control schemes, there are certain special control schemes for special actions. Those are ratio control, cascade control, cascade control. This is for the model development of cascade control systems, override control, split range control, and there is another control schemes called adaptive control. Since we have another paper on process control, that is advanced process control, in next semester, the adaptive control system will be covered under that syllabus. So presently we will discuss about ratio control, cascade control, override control, and split range control. All these are special type of control schemes, and this is under all these are under either feedback control system or feed forward control systems. Ratio control is used for maintaining a certain ratio, fixed ratio, for two fluid flow paths. Say for ammonia plant, fertilizer plant, where for ammonia production, the NH3, the ratio of nitrogen and hydrogen is to be maintained at 1:3 ratio. So throughout the production, the input streams of two fluids, that is nitrogen and hydrogen flow ratio, should be controlled at a fixed ratio, that is 1:3. There are certain other examples like fuel air ratio control in burner, control of ratio of two reactants entering a reactor. A fixed ratio should be maintained. Ratio of two blended streams like ammonia should be maintained at constant. So these are the special applications where ratio control should be applied. Now ratio control is a special type of feed forward control where disturbance is measured and the ratio of process output and the disturbance is held constant. It is mostly used to control the ratio of flow rates of two streams like this nitrogen hydrogen two flow paths, and flow rates of both the streams are measured, but only one of them is controlled. Please keep in mind that two flow rates should be measured, but one of them is controlled and another is uncontrolled, that is called wild stream. Say for this fluid A and fluid B, in order to maintain a fixed ratio, this fluid A, this is the wild stream, and fluid B is the control part. Fluid B is the control stream. So always for maintaining the ratio control, two streams, one should be kept as wild or uncontrolled fluid flow path, another is the controlled flow path. Both should be measured by measuring device. So for both fluid flow path, there is a flow measuring device, and the ratio, that is whatever the desired ratio, there is a divider, then that ratio should be kept compared with the set value desired ratio, maybe 1:3 or whatever. Then the controller is there which maintains the outflow of control path, that is fluid B. This is the most generalized or preliminary configuration of ratio control scheme. Then in next level, the fluid A, this is the uncontrolled fluid flow path, say QA, that is measured with the measuring device, and the desired ratio, that is the set value, is the input here, and the second flow path is the control for the second fluid, that is within a control loop where the measuring device is there. This is the feed forward control scheme. Measuring device is there, and with the comparing with the other fluid measurement and the desired ratio, there is a controller. Accordingly, the outflow of the fluid B is maintained by using controller and final control element. This is purely uncontrolled path, and comparing with the measurement of this fluid along with the set value, the other fluid flow path is maintained as the control flow path with the maintaining the ratio, desired ratio. So that will be the another fluid output, or this is actually the input to the process plant. This is another modified level of ratio control system, and practically this scheme is used for ratio control systems. This is more precise system, that is uncontrolled flow path is measured and the desired ratio is set here. This is for fuel air mixture system. So air temperature is also measured, then ratio is maintained, ratio adjuster was there, then this is compared with the set value, and accordingly, as this is just remember the feed forward control schemes. For feed forward control schemes, this is another arrangement for temperature measurement. Otherwise, this scheme is just like the previous one, where two flow, that is the flow of fluid A and flow of fluid B is measured, and fluid B is the control part. But as this is the feed forward control scheme basically, so along with the measurement of flow, it can take care of other parameter, that is the temperature of air flow path. So initially the flow of uncontrolled path and the flow of controlled path, controlled fluid flow is measured, and maintaining the desired ratio, both are compared. Accordingly, the controller will take action of flowing the control flow path. Along with this arrangement, since this is the feed forward arrangement, so temperature measurement, temperature has an effect of controlling this outflow. So the temperature is measured by temperature sensor, and the ratio, it has a role of maintaining the temperature flow path. So the temperature is measured, and this is set to the sent to the desired ratio comparator. Then it compares three measuring parameters, that is the flow of the previous one, temperature, and then the desired ratio is set, say 1:3, and this is compared with the flow measurement of this one. Then finally that will control the that signal goes to the controller. This is the feed forward controller. Then accordingly, so output path has no measurement and control system. Just note, this is not the feedback system. That's why there is no measurement and control arrangement at the feedback part or output part. So in a block diagram, this is the feedback system where wild stream and manipulated stream, that is the control stream, is there. This is the output variable is measured by the transmitter, and this is the controller. Then the manipulated stream or the controlled fluid flow is adjusted. But this is the feed forward scheme where the wild stream as well as the manipulated stream is there, and the control arrangement is set at the input level, not at the output level. This is here the controller was at the output level, where the desired signal or the process variable is measured and controlled. But here the controller arrangement is along with the manipulated stream, not with the control variable or the process control variable. So this is the arrangement using feed forward system, and as we know that feed forward control scheme is normally used along with the feedback system in order to get better perfection in model. So this is the feed forward along with feedback, that is this portion is for feed forward system, and along with that this output variable is measured with the transmitter, and this is the controller, that is this arrangement is placed here. This is feed forward feedback scheme. During discussion of feed forward control schemes, we have mentioned that feedback control is used along with the feed forward controller in order to get better perfection. That is, if there is any imperfection in the model, if there is any error transmission at the output, that will be taken care by the feedback control system. So this is the feed forward feedback control arrangement for ratio control system. So that's all about ratio control system, and this is the control system for special application. This is another special type controller that is called cascade control. Cascade control is used in a feedback system in order to enhance the performance or to increase the speed of response of the control actions. Say this is a typical example of heat exchanger, where this is the cold water fluid flow path, water inlet, and this is the steam flow path through jacketed pipe tube, and the output, this is the water outlet. The outlet temperature is measured by the sensor, and this is the controller. The set point is given, and accordingly the controller will set the place the control valve in order to adjust the steam flow path, steam flow rate. So this is the cascade control. This is the normal feedback control system for heat exchanger. Now, what is the objective of this heat exchanging process or this control system? Objective is to measure the temperature, measure and control the temperature of this outlet water flow path. So, in order to maintain the temperature of outlet flow path, what we are doing here in the feedback control system? We are adjusting the steam flow path, the steam flow rate we are adjusting steam flow rate so that the temperature of the fluid can be sensed. So we are not changing the temperature of the fluid, but we are maintaining the fluid flow rate. So this is, but we are not measuring the flow anywhere. We are measuring the temperature of the outflow path, and accordingly, as per requirement, we are changing the steam flow rate. But we are not measuring the flow anywhere. This is the arrangement of cascading, where along with this existing feedback control system, there is a internal system where internal control system where the flow of the steam flow rate is measured, and a flow controller is there. This is the temperature controller and this is the flow controller, and so inner control loop is connected here so that the response becomes more faster. Since we are changing the steam flow rate, so steam flow is measured and that is controlled by the flow controller, and this provides the set value to the controller. What is the requirement? Just think about the system, that the requirement is to measure the temperature of this outlet water flow path. So we are in feedback control system, we put here a temperature controller, and what the temperature controller does, that it compares the measured value with the desired value, and accordingly it adjusted the steam flow rate. And when we get the reflection of the steam flow change, steam flow rate change, that when the temperature value changes at this measuring point. So in order to make the system faster, in cascade system, cascade control arrangement, we put here a flow meter, that is the measuring device for this steam flow rate path, and that measuring device is connected with the with another controller, that is the flow controller. Since this is the flow path, so flow controller and flow measurement, this controller will be much faster than the outer one. And for this system, this controller output acts as a set point to the flow controller. So this is called the cascading. So there is a primary controller, that is a temperature controller for this heat exchanger system, and within this there is a inner loop, that is a secondary controller, that is the flow controller, where flow measurement and this is the final control element. So there is a inner loop within the external outer one. So there are two major functions of the cascade control: to eliminate the effect of some disturbance and to improve the dynamic performance of the control loop. Since inner loop is see, this is the temperature controller. So temperature system is much slower compared to flow system. So as this is the faster system, so the dynamic performance will be improved, and the other disturbances due to flow rate change or steam flow path, that will be measured and controlled by the inner loop. So effect of disturbance arising within the inner loop is corrected by the secondary controller. What I am trying to tell, that the disturbance is due to the steam flow rate change, that is within the inner loop, that will be corrected by the secondary controller, that is the flow controller, before it can influence the output. Before that actual temperature change, since the inner loop is much faster, and the primary controller takes care of the other disturbance in the outer loop, and as a result the transient response of the overall system will improve. Say this is the normal PI controller response, and the cascade PI controller response is much where the oscillation is less compared to the normal feedback part. That is much more smooth operation compared to feedback. So the advantages: a strong high gain input system, inner loop reduces the sensitivity and non-linearity of the plant in the closed loop. Always you should keep in mind that the inner loop should be chosen in such a way that that should be of high gain system, much faster system. Say for temperature controller, for this example, the outer loop of the primary control system is the temperature control, and the inner loop is the high gain system and faster response system, so that the disturbances occurs in the inner loop can be reduced before reflecting at the outer loop. That is the objective of using cascade system. Otherwise, if the outer loop is slower, outer loop is faster and the inner loop is slower, then it will affect nothing. So the inner loop must have high gain system so that it can reduce the sensitivity and non-linearity of the plant. The outer loop therefore experience less parameter perturbation. And cascading makes the use of feed-forward control more systematic. That is, in heat exchanger example, it is possible to measure the water flow and add feed-forward compensation. That is, if we use feed-forward compensation along with this, that will definitely improve speed of response. But even with this feedback system and cascading, it will improve a lot. Cascade control often makes it possible to use simpler control action than what could be needed for a single controller. So the number of tunable parameter is more in cascade control. A systematic tuning procedure is available. This is the process that if we have only one controller in a control loop, then the tuning of that controller is sufficient. But since there is a second controller, a secondary controller, which have higher gain than the outer loop, so the tunable parameters are more, since the number of controllers is more than feedback controllers. So a systematic tuning procedure is available. But the disadvantages are more number of devices, that is number of sensors, transmitters, controllers. So the effective cost of the process is higher. For proper operation of cascade control arrangement, the dynamics of the inner loop should be considerably faster. This is that I want to mention repeatedly, that the dynamics of the inner loop should be considerably faster than the dynamics of the outer loop. Otherwise, it does not have any effect of cascading. The inner loop secondary controller is normally chosen as a simple P-type controller with high gain, and outer loop primary controller is conventional PI controller, because PI control action is mostly used for control systems. So the block diagram and module is like this this is for secondary control system. So GC2, GP, this is the process GP2 and this is the process GP1. This is the primary controller, and if we obtain the transfer function, the inner loop, the roots of the characteristics equation is this much equals to 0, and that must be on the left hand side of the S plane. On the other hand, for maintaining the stability of the primary control loop, the roots of the equation, that is for the whole system, this must be equals to 0, and this is on the left hand side of the S plane. It is often advantageous to make the inner loop 3-4 times faster than the outer loop. So inner loop should always be high gain system or fast system compared to outer loop. Next type of special control scheme is split range control. Split range control is a single output variable but several manipulated variables. That is, the coordination among different manipulated variables is carried out by using split range control. Say there are number of boilers. From all the boilers, the steam header are, say for a processing unit, the steam header, the required steam header should be generated from number of boilers. So all these are collected in a single header, and all these boilers output, that is the final control element, is connected with the same controller. That is, this is the transmitter. Steam header means pressure measurement, so pressure measurement and pressure controller, and that is divided or splitted to control different boilers output. So all the outputs are controlled using same header, same controller. This is called split range system. The steam discharge from several boilers are combined at a steam header. Overall steam pressure at the header is to be maintained constant through a pressure controller. The command from the pressure controller is used for controlling simultaneously the steam flow rates from the boiler is parallel. So there is a single output variable, that is the steam header pressure, while there are a number of manipulated variables, that is discharge from different boilers. The output of the steam header is the steam pressure. That is by that the different manipulated variables are controlled. That is the boiler discharge of all the boilers. So in number of boilers, discharge are controlled by a single steam header pressure. So this is the splitting or split range control. And override control. Override means, say for feedback control system, say this is the control scheme for uncontrolled inflow system, and the output is a controlled flow system. How we have used the feedback control in order to maintain the controlled fluid flow, constant fluid flow at the output. That is, we used to measure the flow rate. Then this is the flow measuring device, flow transmitter. There is a flow controller, and accordingly the outflow is controlled, and as a result a constant level can be maintained. So by controlling the flow rate, there is a flow measuring device and flow controller. By controlling the flow rate, we are ultimately maintaining a fixed level at the storage tank. Now this is the scheme called override. That is, our requirement is to maintain a certain level of the tank. Not only the upper level only, level control, I mentioned this earlier also, that level should be maintained upper level as well as the lower level, so that the dry run cannot happen in a system. So the upper level and lower level, so the symbol is this one for level transmitter in order to maintain upper level as well as the lower level. So there is a level, we are maintaining the level of the tank by controlling the flow system, flow control system. Along with that, there is a level measuring system and there is a level controller that selects the selector. This is the selector, this is another controller, but this selects that in particular situation it may choose flow controller or level controller depending on requirement. Say, when level goes below the upper set value, then the what will happen? When it goes below the upper set value, then the pressure at this column will decrease. Accordingly, the flow rate will be changed. So, in turn, the path will get closer and the flow rate will decrease. But the selector switch instantaneously selects the level controller first as it changes the level. So this will take the corrective action instead of the flow controller initially, and the selector will transmit the controller output to the control bar. This is the function of this. This is called the overriding of this controller functions using another level of controller. So this is used for delicate systems where due to small change of say level or other parameter, it may get affected. Now process plant production may get affected. For these systems, along with the existing control system, there is a overriding element for selecting the controller output in order to get faster response or quick response. So there is another, there may be another level of controller for lower level also. This is for upper level. So for lower level also there may be level another LIC for, this is the element of for minimum maximum position. For say maximum position, there is a level 1 controller. For minimum level, there is a level 2 controller, and there is another selector switch, another selector controller. See, this was our initial feedback arrangement flow controller system. There is a selector, and this selector selects the, normally it runs with this flow controller path, but if level changes suddenly, then the selector will transfer the level controller output to the control bar, and if it for upper level, then it will choose the upper level controller output, and if it for lower level, then it will choose the lower level controller response. So in order to choose lower or upper level, there is another selector controller FYC. So this is for delicate system where minute changes in process variable may affect the production, because this is otherwise if it works with this feedback control system arrangement, then why we will use so many devices, two controllers, two selectors, these are also controllers. So there are number of devices along with the existing control systems. So this is special type control system or override control. So that's all about our four type of special control schemes: ratio control, cascade control, split range control, and override control. So that's all about special type of control scheme. Thank you.